Okay, good afternoon.
Salam.
Today we are going to continue on sand management. In terms of a quiz discussion, I think still not the majority is thinking about this. We can do it when everybody wants it during this week. Maybe tomorrow, maybe on Wednesday. But the main thing, we have to complete the program, and then we can discuss it. We will discuss anyway, because I want also to discuss it, to point the main issues that you have, well, we have with the questions and answers. And so we can do it probably Wednesday. Hopefully by that time we will finish the program. And so we can do it with the easy way, without any pressure on the program. Okay, is that okay? So let's continue on the sand production. Last time we talked about the what is the sand production and causes of the sand production. What happens if we do not install sand control methods, sand control equipment, and or what happens if we unnecessarily install it. And we talked about sand production, the reason that sand production occurs. The mechanics, how the sand mechanism of sand production occurring. It starts in the reservoir, then it moves into the perforation tunnels, or if it is perforated well, or through the open hole, and then some of them are lifted up to the surface, and some of them are accumulated in the wellbore. So the ones that are accumulated in the wellbore are filling the wellbore and creating additional mechanical skin. The ones that are lifted up, they are causing the erosion and the fill up of the surface equipment. This destruction process of the sand cementation or sand grains into the fine sand movement is related to the drawdown as well. As the sharp increase happens, then this destruction may involve additional sand detachments, and also the sharp change in drawdown can disturb these bridging elements of the sand, and then these bridging elements that are preventing more sand going into the wellbore will be destroyed as well, and then again another influx of sand production will be seen in the wall product. Okay, and we talked about the forces acting on the sand grains. So the effective stress, which is related to the overburden, pressure, capillary forces, pore pressure, that is kind of resistant to this effective stress, and the drag forces when the fluid becomes mobile, fluid becomes starts moving in the reservoir as we start production. And when the balance between the effective stress and capillary force is the pore pressure is changed, or in other words, when we start production and pore pressure reduces, then drag forces are getting into play and moving the sand grains that are very weakly consolidated. And that depends on the fluid viscosity, the fluid velocity, which is a kind of a representation of production rate. And also it might be some destruction of the cement material by the water production, or due to some chemicals injected into the reservoir. And here we have a completely weak or unconsolidated reservoirs. The reservoirs with the strong consolidation. In first case, we have certainly we know that we will have a sand control required. In second case, we may be sure that there is no expected sand production, although this might be not true when we cut the water and or we start some acidizing processes, but still it will be around the wellbore. And the most important, most problematic area is the intermediate. And in this area, when the consolidation is not so strong to keep everything together, and but also not so weak that we are sure that this will be producing. In this case, the question that we asked in the beginning, should we put the sand control in place or not, is becomes very difficult question. And as we said, the wrong approach in this may turn to the disaster in terms of either production and the environmental manner, or budget and capex NPV side, both respectively, if we omit it without looking into the root of the problem, or in the second case, when we install it unnecessarily, so we will have a great wasted finance or budget on these issues. The continuous sand production is when we start producing sand, it continuously increasing. Cleanup sand production is what we when the sand is produced in the situations when we change the rate or increase the drawdown, open the choke, and in that case the weak sand is become because of the stress change within the reservoir. The mobile fines are dragged by the dragged and drawn by the fluid movement, and as the production stabilizes, the reservoir condition stabilizes, the sand going down, sand production reduces as well, and as you can see here, it is kept at the lower values which can be handled at the surface. Consequences of sand production, as we said in the reservoir section, in the reservoir part of the well, is the wellbore field, which is loss of productivity. As we lost the productivity, we produced less, so we lose the reserves, and as we produce less, we come to the economic limit earlier, so we lose the reserves or the total amount of oil that we can produce. Subsurface equipment is the sand filling in the tubing, so we will not be able to wireline operations, PLT, or any logs, any intervention job, and of course erosion of the some valves, other accessories of the tubing in the tubing string in the upper completion, and the surface, as we said, sand accumulation, again erosions, especially in flow lines, in T-bends or elbow bends of the pipelines. Sanding impact in various environments are shown here. How it is, it should be approached in different areas. For example, for gas or gas condensate and high pressure, high temperature wells, gas is very dangerous, very bad, because with gas it has a high velocity and high erosion rates. For the subsurface wellheads, depletion drive reservoirs, horizontal wells, injection wells, it is also kind of concern, and it should be very well designed for to resist the sand production, to be able to handle sand production, because subsurface wellheads, if first of all loss of production, but even more importantly, it is very vulnerable to the environment. If we have any leak on the subsurface wellheads, then it might be very dangerous for the environment. But of course, again, on the other side, of course, the production also will be suffered. Depletion drive reservoirs, because as we will see later, as the depletion increases, the pore pressure reduces, and because of effective stress is increasing now, is dominant, then the strongness of the strength of the rock is getting reduced, and that may cause even more sand production, or it may cause a some kind of compaction of the reservoir, which means we will lose the porosity, permeability. Horizontal wells, injection wells, these are very also vulnerable to the sand production. We may talk about that if you like. And separator functioning, we told about separator filling. it might be some sort of well, let's say not profitable, but favorable for low PI wells, as the sand production from low PI wells first of all created cavities around the wellbore will increase the effective wellbore, and the PI will be productivity will be increased. And for heavy oils and asphalt and scale wells, they also are maybe favorable, because with the sand we will produce all this, especially for heavy oil. There is a technology called CHOPS, called heavy oil production systems. This assumes producing heavy oil with the sand, and then on the surface with the PCP pumps, and these oil with sand. The sand is separated from oil, and then cleaned and disposed. And oil is sent to the refinery or processed in another way. So, therefore, sand management is very important issue of the petroleum engineering, production engineering, and petroleum industry at all. The sand management is kind of two-part or twofold problem when we have two ways of approaching. Vishal, do you have a question?
Yes, Ilham, madam. I would like to ask about the effect of sand production on PCP. I mean, how it can add some positive aspects on the result, profitability.
This is not about PCP, this is about heavy oil. Heavy oil reservoirs are very viscous oil, are containing very viscous oil. So its mobility in the reservoir is very low, and we use PCPs to produce this heavy oil with sand. So we are producing oil with sand. So because it's very viscous, it brings the sand with the oil. It brings sand with it into the wellbore, and this sand is produced as well. So here it's meant that as we produce sand, we increase the wormholes around the wellbore, or we increase the cavities around the wellbore, and it's kind of becomes a matrix flow into the wellbore area, which is essentially cavities. And then as we produce more sand, more cavities and more wormholes in the reservoir, so the mobility of this viscous oil becomes higher. Did you get the answer you wanted? Did you understand it?
Actually, yes, but I would like to ask one more point about the, let's say, the flow rate. So it means that the flow rate is low, and
yes, of course.
Yeah,
it cannot be 1,000 barrels.
Okay.
It is within maybe 100 barrels. 100 barrels. Some 100 barrels, not many. Okay, up to 1 or maybe 200 barrels per day. Yes. Well, even 200 barrels might be questionable, but yes, in this order. Of course, the rate of these oil wells are not so high. Okay. So dealing with sand, we have two options. One is called a prevent sand production. By monitoring the well flow rates and drawdown, or permit sand production and plan for handling, disposing of produced sand. So prevent sand production includes a sand exclusion methods as well, applying the sand control completions. We will talk about this later, different sand control completions that prevents the sand influxing into the wellbore. So we try to keep the sand inside in the reservoir part, or by mechanical methods, or by monitoring and controlling the well flow rate and drawdown, or let the sand to be produced and plan for handling and disposing of the produced sand. Both of them are requiring some the appropriate approach. So both of them are related to studying the reservoir properties, sand characteristics, and specifics, the well rates, the project or development options, and based on those, based on this analysis, based on these studies, we can decide either of them or some combination of these two approaches. Let's talk about one by one, starting with living with sand production. What is living with sand production? It means so we allow the sand to be produced, and we get ready to handle this sand at the surface. And here we have to admit or accept the risks associated with this, and understand those risks, and think about how we can minimize the effect of those risks, or prevent or eliminate the effect of those risks, like erosion of tubulars and surface equipment, again, especially when the high velocity gas production is the subject. Sand fill can also interfere with the use of corrosion inhibitors, meaning that the corrosion will be less effective, reducing effectiveness of lifetime of artificial lifts, in a way that, as we talked last time, any solids will get problems for the artificial lift, fill the completions, obscuring lower intervals and limiting well intervention, filling surface equipment such as separators, interference between with the sealing valves, sealing of the valves, and operation of instrumentation. These are the maximum sand, the allowable sand levels for different fluids and different rates. And to accept, when we choose this approach with dealing with the sand production, we have to make sure that we set up effective sand management system and sand tolerant production system, so we don't get this situation in our production system. This is a completely eroded chalk. You can see this is the chalk. This is the housing, and this is the choking element of the chalk, or the stick in the chalk that is restricting the rate of the walls. So it is completely eroded by sand. So this system should conclude the modified artificial lift methods. In other words, we may use some harder materials that are interacting with the flow, like impellers or diffusers in ESPs, or standing the traveling valves in other pumps and other moving parts of the artificial lift equipment. Install hard-faced chalk to be more resistant. Remove 90-degree or T-way, T-form, T-shape piping bends, because these parts are mostly vulnerable to erosion, as it is a hitting point in the flow direction. And of course, monitor pipe condition, the thickness of the wall, and is there any erosion on the inside to the pipe material. Measure sand production, installing sand monitors or other laboratory methods. Surface sand collection and disposal facilities should be ready to take this, cleaning the separators, or the not allowing the separators to be filled by separating the sand before entering the separators by sand hydrocyclones, and of course manage the well production, cleaning up or the increasing the drawdown or rates on the reservoir, slowly, moderately, maintaining constant flowing bottom wall pressure, so there is no disturbance to the stress in the reservoir, and no triggering events to the to start sand production. One of the questions here: will the sand be produced to the perforation, from the perforations, and transported to the surface? Because now it is kind of a subject or issue, because if this sand will be continuously filling the wellbore, then we will have a problem with the well productivity. We will have a problem with the frequent well intervention to clean up or wash out these sand accumulations. And here you can see some kind of experiments, or the predictions for some North Sea fields. They tested at different rates, 2,000 cubic meter, 1,500 cubic meter, and 500 cubic meters, and against the depths that the sand will be produced, against the sand grains diameters. And that is showing that, as would you expect, but it is kind of a guidelines that the larger the sand grains, the shallower these grains can be transported. Shallow depths these can be transported, and also the rates. The higher the rate, the larger the particles can be lift up or transported up to the surface with this rate, because now as we increase the rate, the velocity of this flow is increasing, and we get higher, larger particles. The flow is able to flow the larger particles. But as the depth is increasing, then we can see that the difference between them are getting smaller. So there is some kind of depth limitation from which even smaller sand particles cannot be lifted up or transported up to the surface. The implication of this is that we have to, before deciding on which way we want to go, we have to decide, we have to analyze the sand specifications, sand characteristics, or reservoir properties. What is the sand grain sizes? How we should deal with that. In the second diagram, you can see the grain diameter against the velocity of the grains, and the within the tubing, a 5.5 inch tubing for different rates. So that is again as the velocity changes, the possible as the rate changes, the velocity of the size of the grain, the diameter of the size of the sand grains are increasing, but still it is getting lower because the sand itself, as a part of the flow, now kind of creating a slowing factor. Okay, so therefore this is the larger the grain size, the higher the effect of sand on the velocity of the flow itself. This is a kind of a modern living with sand installation or infrastructure. So we have a production well, then the production goes through the hydrocyclone that are separating dense sand grains. It goes to the sand line and then sand cleaning unit. And the production, the fluid goes through the choke into the sand detector to monitor the sand production, and it goes to the separator. Of course, some fine and light sand particles will fill up in the separator, and that can be again disposed by these valves or water jets that are flushing this sand through these valves, and it joins this sand another hydrocyclone going through these hydrocyclones, and the kind of it's something like a knockout drum for the gas or liquids. Here we knock out the sand grains, the smaller sand grains and the other sand grains, and the sand grains that are coming from the main hydrocyclones, and then cleaned water is going to the water treatment and the final oil removal part, or the line, and the cleaned water is injected into the reservoir or disposed to the sea, and the sand is also, after the cleaning, is disposed either to sea or transported to wherever it's planned or designed to be disposed. This is an example of sand monitoring and keeping the sand by the monitoring the rates. And here you can see two wells. This well is the producing, and this is the choke of this well. And as you can see, as we increased the choke, the sand from this well is increased sharply. But as we keep this stable, the sand goes down. And now, as we increase the rate at the small steps, sand doesn't increase that sharply. And here, at the stable choke, we have just some peaks of the sands, which are again leveling down and stabilizing throughout the constant choke or stable choke. Okay, and here in the next, in the other well, you can see that as we increase the choke here, again the sand production is increasing, and then when we shut down the well for some reason and open the well again, the sand is peaking and then stabilizing for some period, as we have a more or less stable production. So as we said, this option is requiring the monitoring sand, and monitoring sand is done by acoustic sensors. Which is installed on the externally, usually after the bends, because this part is mostly getting. This is the part which has most noise because of this direct hitting the wall, and this is the part that is mostly vulnerable to erosion. And here we calculate monitor the sand production. And this is a kind of filtering the sand noise from the other noise, the flow generated noise, and based on this filtered noise, we also measure the sand at the end of this line, and we can adjust, or we can kind of formulate how we measure this sand production. Living with sand production is another way of monitoring sand, is having a X-rays, and which is measuring the sand level, and as it comes to this the control level, the separator, the sensors are giving the signals, and separator is taken offline, so the production through this separator stopped, and high velocity jets fluidize sand from at the bottom of the vessel. But in many cases, at least years ago, people would do it with shoveling. So just operators would go in and shovel out by hand this sand from the separators, which is of course very dangerous job because of confined space, because of kind of the atmosphere in these separators. So it's kind of a non-pleasant, non-safe job. So now it's mostly done by water jets. It's washed out through the valves that are opened from the bottom of the separator. So therefore, the prediction of sand failure is very important to understand at which level or how much this prediction, the failure is expected, and what can be the level of this failure, what can be the level of sand production to make a decision on the choosing the option to deal with the sand. And here we have a few approaches, like a field experience. So having some analog fields or the same field experience from the first wells or appraisal wells. Of course, there is some on-site rock strength measurements, estimations, laboratory measurements. On-site usually are looking at the core samples, how the core samples are weak or strong, or how the core recovery is at all. Can we get the core, or in very unconsolidated, very weak sands, even getting the recovery of the rock is a problem, because as you open the core carrier, the rock is just like a sand in here, and this is not representative, not any measurements can be done on this, because this is just a destroyed sand particles. Laboratory measurements include Brinell, the measurements of the strength with different methods, like Brinell methods, unconfined compressive strength, thick wall cylinder collapse strength, petrophysical log, and core analysis. Okay, field experience includes as I said, the fields or with the similar geology, similar reservoir rock, and the production history experience. What is the sand-free rates? What are the drawdowns at which the critical drawdowns at which the sand is started to be produced. One of the testing is Brinell testing. This is not in your book. Strength of the formation can be evaluated according to the Brinell scale. And Brinell testing is this kind of apparatus, and then you put this the sample on this plate and lift this plate up to this ball. It is a ball at the end of this device, and this ball, it is pushed against this ball until for 15 seconds or so, until it creates this indentation on the material. And depending on this pressure that we applied and the relationship between the diameter of this ball and the indentation, we can we can obtain the Brinell hardness number. This is one of the rock strength evaluation methods, and from the relationship between the Brinell hardness number and the rock description. You can see here when it's less than 2, it means this number is less than 2. That means it is unconsolidated. When the pressure, the ratio of the pressure over these diameters is very low. So at very low pressures, it will create high diameters, high indentations, the large indentations. So it is unconsolidated. So no cementing material between the sands and etc. Partially consolidated, friable, consolidated, and hard, which means very hard, very well cemented sandstones or rock. Unconfined compressive strength test is done when we place the core sample or rock sample between the 2 plates, and this plate is stationary, and this plate is pushing on this rock sample, and we increase the pressure until the sample fails, or the destruction of the sample happens. You can see here we lost this half of this through this line, and these sample failure pressures are recorded as a uniaxial or unconfined compressive strength. And when we compare this unconfined compressive strength or uniaxial compressive strength, we can see that it is it can be correlated with the porosity of the same formation. Okay, so different cores with different porosity values are tested with the unconfined compressive strength test, and then the results are showing that the porosity and strengths are quite strongly related. And here we can see again the table where we can compare with the strengths, evaluate the strengths, the uniaxial compressive strengths against the rock classification or description. Here you can see if it is 0, it's quick sand, or as I said, you can't get any core from this. It's just a it's just like a dust form sand, unconsolidated. We have no apparent cement or easily crushed, and the harder you cannot crush, and the approximate sonic travel and the core recovery is excellent because when you do coring, you can get all this material as it is from in the reservoir. There was another. This is not also in your book. There was another study to show the compressive strength and the drawdown effect on this strength on this rock failure, and these studies showed that the rock begins failure when the drawdown pressure, or the pressure between the reservoir and wellbore, is 1.7 times of the compressive strength, and this is put on the graph to show the relationship. And this almost linear strength show the slope of 0.6, which is reciprocal of this 1.7. So from that, it was concluded that the drawdown must be larger than compressive strength by 1.7 times. And this is the results of this drawdown effective experiment. This is the early results when we produce some fluid oil through this sample, and this is cavities formation in the rock sample as we produce, and this is the end or completion of test. At the end of the test, this cavity is even much larger than at early time. So it's taking some sand, and of course it will depend on the compressive strength of the rock. And this is another kind of a estimation which is done in Norwegian, in the field of Norwegian sector of North Sea, in HPH, high pressure, high temperature wells. It shows the critical drawdown values, above which the sand production occurs. So this is the critical drawdown. So in very simple saying, if we apply drawdown more than 600 or 550 bar on this rock, then the sand production will happen. But this is also showing that as we deplete the reservoir, as we produce from the reservoir and reservoir pressure reduces or declines, this critical drawdowns also declines. So if our reservoir is depleted by 300 bar, or reservoir pressure is down by 300 bar, then the critical drawdown is about 200 bar, which means the now pore pressure is so low that the drag forces and the overburden pressure is just taking overburden pressure is destroying the reservoir, the rock, and the drag forces from the flowing moving fluids are detaching the sand grains, and the sand production is increased. Okay, thanks for your attention. We'll stop here because now we passed the time. Do you have any questions? Hello? Parviz, do you have a question?
No, sorry.
Okay, I will, of course, discuss these results because it's the the aim of these quizzes are, we will try to make another one if we can, but let's see how it goes. The aim of these is to see how you are doing the course, how you are progressing, how you are learning, and more importantly, how do you take these questions. Unfortunately, there are some problems with understanding questions, with the answering questions, especially in online conditions, and we will talk about that. Okay.
Okay, Ilham. See you
Those
tomorrow.
are the quiz was very easy. It wasn't extraordinarily difficult. Okay. The exam will be much difficult. And this is another issue that I would like to discuss. Okay. It's much better to learn to study this subject rather than looking into the book to find the answer. That will take your time, and that is easily spotted. I can tell everybody who just copy paste or just typed the answer from the book. It's easily spotted. Okay. See you tomorrow. Have a good time.
Thank you.
Sağ olun.
Sağ olun.
Sağ olun. Sağ olun.
Sağ olun.